Hello, welcome back to our channel. Today we are going to discuss about using an operational amplifier in a open loop and closed loop configurations. So we know that op-amp can be used in feedback circuits, and that is the advantage we get when you use operational amplifier in a negative feedback. So there are two basic types or configuration of using op-amp, that is the inverting and the non-inverting circuits. So we have discussed in our earlier videos about the theory in which we use the operational amplifier circuit in a inverting and non-inverting, and we derive the gain expressions for the gain. We also discussed the input impedance, differential input impedance, offset voltage, closed loop gain, frequency response, etc. But right now in today's topic, we'll actually apply that theory and design them and simulate the responses, and we'll analyze our understanding. So what I'm going to do is from this using this circuit simulator, I am going to pick up the components. For example, right here you see here there is this component library. So I am going to actually use this. Click here, and here I am going to use an operational amplifier called as universal op-amp. So I can use another variants of these, but basically the very basic is this one. Here it is reading that it is a linear single pole op amp. It means it has a frequency response of a low pass filter. So for example, the operational amplifier frequency response can be drawn like this. So the single pole, it means here is your pole frequency, uh, FC, and after that the gain drops with the rate of minus 20 dB per decade. And here is your frequency, and here is your gain actually. And it says it's a linear single pole op amp with no internal nodes or output voltage range limit. So your output at the end of this operational amplifier can have unlimited swing. So obviously it's not a practical op amp. There are practical op amps which are given here, but for illustration I'm going to use this very simple, and that's why it's called as universal op amp. I can set my own parameters. Now this simulator also offers me to open this circuit's micro model circuit. So as you can see that it is prompting me to open this macro models example circuit. So what I'll do, I'll click here, and right now here is the circuit. So before I explain to that, I would just clear all the drawings that I have done, or clear my drawings, something like. So what I see here, here is your operational amplifier with the gain A, and the parameters of this amplifier has been set. AVOL stands for open loop voltage gain. When there is no feedback, you have a gain of an amplifier without any feedback. So you just have operational amplifier with negative and positive input, call it V1, call it V2, and you have output, and there is the gain. Then you have this gain bandwidth, which is set to be 10 mega. So gain bandwidth product is the product of your gain and the bandwidth. So remember, and it has a value of 10 into t to the power 6. So when you use operational amplifier in an open loop, so gain for that, let's say gain in an open loop is, for example, 1 into 10 to the power 6. So in open loop configuration, you will say that the bandwidth can be calculated by this equation. So bandwidth would be 10 to the power 6, this parameter, divided by 1 into power 6. So it is 10 hertz. 10 hertz, yeah. So the frequency response can be drawn like this. So you have like, this is your frequency, and yeah, so, and this is your gain of this value is 10, and this value, oh, this is 1 into 10 to the power 6, and this frequency value is 10 hertz. Okay, so you see there is a very huge gain, but the frequency is only 10 hertz. So you can apply signals to this operational amplifier within this range, 0 to 10 hertz. But when you use a negative feedback, where you actually want to use the operational amplifier in a closed loop circuits, for example, inverting and non-inverting, which is today's discussion, we'll see that your gain bandwidth product can be constant again. So let's say you have a gain for a closed loop. I will call it closed loop gain, which is you want it to be 10. You want now the gain to be 10, and gain bandwidth product is always constant. I said it is 10 into 10 to the power 6, 10 mega. So now you want to give me the bandwidth again. So bandwidth would be 10 into power 10 to the power 6 divided by 10, the value of 10. So it would be 1 into 10 to the power 6 hertz. So in that case, your frequency response can be drawn like the gain is now 10, just a 10. So it would be like this. Let me draw this, and it would be, this is your x-axis for the frequency. But now you see, or the green curve indicates your response of an amplifier. So gain is a 10, and the frequency right here is 1 into 10 to the power 6. So 1 megahertz, up to 1 megahertz signals, having the frequency up to 1 megahertz, you can apply to amplifiers with a closed loop. Now, the circuit that is shown right over here is a circuit of a voltage follower, because at the positive input, you have a pulse that you have applied, which has amplitudes varying from 50 millivolts to plus 50 minus 50 millivolts to plus 50 millivolts. It has on time about 250 nano, duration is 1 nano, and we'll see those parameters. And so it just you have a this pulse right here. Okay, and to the negative, you are basically feeding all of output to the negative here, right? And having said that, then you have a load, which is R1 and C1 in parallel, 10K and 10 pico respectively. So yeah, so before I move further, I forgot to explain you other parameters. Here is your VOS is a offset voltage, which is zero, set to be zero. Then there is a differential impedance of op amp. So remember, you have two terminals of op amp, and then you have this REN, that is the differential, or RID, that is the differential input impedance, which is still very high, 500 mega. Then you have this, if you recall the theory circuits of the operation amplifier, the equivalent circuit, it has a voltage source, then current source, right? What is E and K and I and K, you need to refer to the SPICE model. So anyways, I have explained you the concept of gain bandwidth product, which is constant always in this case. Now, your gain is 1. For example, your gain is 1 because your output is equal to input based on the theory. What we say, if the gain is very, very high, open loop gain of the op amp, let's say 10 to the power 6 or 1 to the power 6. Here it is 1 to the power 6. So it means your difference of the inputs is approximately 0. So if the gain is very high, so you have a gain, which is the ratio of output by VID, differential input. So if gain is very high, VID, which is the difference between V1 minus V2, is equal to 0, right? If gain is very high, if this difference is very, very less. So if ideally we'll say that if it is infinite, then it has to be 0, right? So it means if there is no difference between the two inputs, whatever you apply at this positive terminal, same goes here. And that means that signal is appearing at the output. So V out is equal to V in, right? And in that case, your gain is 1, right? Let me just see that. V out would be gain times VID. And just a minute. Yeah, so in this circuit, we know that V out is equal to V in. Therefore, V out is divided by V in is equal to A, and V out is equal to V in. So we know that V in divided by V in is equal to A, which is gain is approximately equal to 1, right? Because V out is equal to V in. And now these are the two power sources, that is plus minus 15 volt, that is applied to the negative and the positive terminal. If you simulate the response for this circuit, you will see output will try to follow the input. So we'll just see that the input has been given. Before that, I will just explain you how right clicking this, you see that the independent voltage source is chosen to be pulse, which has an initial voltage of minus 50 millivolt, then turn on voltage is plus 50 millivolt, delay of about 250 nano seconds, rise time 1 nanoseconds, fall time 1 nanosecond, T on is 1 microsecond. So the pulse is on for 1 microseconds and the period is 2 microsecond. So for T off time is also 1 micron, and there are no cycles mentioned. So click OK. And then I can see that there is a transient analysis that is being applied, that is being asked. So here is the syntax for the spice.tran, and it has been asked to run this analysis up to, I will right click it, and I see the stop time has been mentioned here to run the analysis up to 1.5 micron. So it is performing a non-linear time domain simulation on this circuit. So we'll just see that. So click OK. And now I will just click run. And it opens up the waveform window. Before that, I would like to clear the viewer's drawing, maybe, or clear my drawing here. And now what I want to plot is plot the input signal, that is source V3. And here I can see that uh, I have this pulse, which is on for up to 1 microseconds. And then I will then click on the output. So right now, the input signal was the practical voltage source and the output is following. And this blue curve is our output, which has a slew rate. Slew rate can be computed, that is change in voltage with respect to time, dV by dt. That is one thing. So you can now do some analysis on the right click here, and you can actually see that add many other traces also. So for example, I want to add plot pane here. Now, since this is a voltage follower, I want to measure the voltage at the negative, which is actually nothing but the output voltage, right? Voltage at the negative terminal, right? Then voltage across R1 and capacitor, which is the load, is gonna be same. How about I want to run the DC analysis? I leave it to you. We have done that before. So for example, I just delete the stress and then Now I want to play with the op-amp parameters. For example, I right click the operational amplifier. Here are those parameters. I want to set it to be 1 mega, but now I want to just have it 10, and we'll see what happens. So 10 is very low gain. And now I will just click the button here. And do you see the difference? The output has changed. Before it wasn't the case. Let me just undo and rerun the analysis. And now output is perfectly fine. Let me delete this pane right here. I redo the things again. Okay, let me just here 1 mega. Okay, let's have about 10 here. And then we'll run the analysis, see how the output is changed. Output is no longer the case, right? It's about 50 millivolt and output is less. Also, there is a difference over here. So the gain is not to be changed to very low value. What about I change the bandwidth? So I have a signal about uh, one, let me see the T on time is about period 1 micron. So 1 megahertz is about 0.5 megahertz is the frequency of this pulse. So because time period is 2 microns. So what I'll do, I will just right click. I will try to change the gain bandwidth to be, let's say, it's 1 mega, and we'll see if there is some problem in the output. Yeah, you see now your output is not following the input. Output is not following the input, and that could be the situation. And that could be such situation. What I'll do, I will just keep it back to 10 mega, and that is how I will just do it. And it's perfect now. It's showing the way. Just try doing those experiments and you will see the difference. Okay, change the offset voltage also, change the input impedance. For example, if you have a very low value of input impedance, it's not 500 mega, but just 500. See what difference it makes on the response of this. Not much, it's not visible. So just try to do that, but bandwidth is making a difference. Similarly, change the offset voltage, change the pulse to sinusoidal source and all that. So in the second part, we'll explore some inverting and non-inverting configuration. Till then, stay tuned for more contents. If you like this video, click the like button, comment on the video, share with others for a wider reach. Stay tuned and wish you happy learning.